Okay, so now we are going to solve a problem which has been very frequently asked in interviews. Okay, so we will be given a binary tree. Okay, before we move ahead, let me ask you a very quick MCQ kind of question. So we have a binary tree, okay? We have a binary tree with n nodes. What can be the maximum value of its height? Yeah, maximum value of the height will be n. And when will that happen? That will happen if all the n nodes are lying along the same line, which is the case of a skewed tree. Okay, my next question is, what will be the minimum value of height of a binary tree? Let's take example only. Let's say n is equals to 7. If n is equals to 7, you have got 1, 2, 3, 4, 5, 6, 7. 7 nodes along the same line. Here the height is 7. And if there are 7 nodes, just you take out your pen and paper and tell me what will be the minimum height. Minimum height will happen when you have got a perfect tree. This case, here the height is 3. Yeah, and I had told you that when you have got a perfect tree like that, comprising of n nodes, then the height of this is log of n base 2. Correct? So I can say that if there are n nodes, then the minimum value of height will be log n base 2, and the maximum value of height will be order n. And it all depends upon what is the structure of the tree. If it is skewed, it will be a tree having huge height. And if it is perfectly balanced, then it will be log of n base 2. It's an important point. Is it making sense to all? Yes or no? Let's look at that question now. We have been given a binary tree, and what we want to do is we want to print all the root to leaf paths. Print all the root to leaf paths. So let's say your binary tree is like that. How many root to leaf paths are there in this tree? There are 3 root to leaf paths. Can I say that number of root to leaf paths will simply be equal to number of leaves? Isn't it? Like, see, there is only one root, but there are multiple leaves. So this is one path. So this is 3, 4, 5. And this is another path. This is 3, 4, 7. And that is the final path, which is 3, 2, 9. So similarly, there can be multiple root to leaf paths. I want you to write a code which prints this data, which you can see right now on the board. This is a problem which you can easily solve using recursion again. So let's look at the board now, everyone. This is quite important. Let's say there is a big tree, okay? There is a very big tree. I'm just drawing a small portion of it. So let's say it has an edge coming from some node, and here you have got a 4, and here you have got a left subtree of 4, and here you have got a right subtree of 4. It's a big tree, by the way, okay? And there is root somewhere. Let's say root is present over here, something like that. Now, answer me one thing. There will be some root to leaf paths which are present in this left subtree. When I say present in left subtree, I mean to say that there will be some root to leaf paths whose leaves are present in this left subtree. And there will be some root to leaf paths whose leaves are present in this right subtree. Can I say all such paths that cross this 4 and land here, 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 or here will have 4 in them? Just think, any path that goes like that, that, or that will definitely have 4 in them. So it means that if I am there at a node, let's say I am doing a recursion on this tree. I'm visiting the nodes one after the other, okay? And I'm doing that using recursion. So if let's say I am at 4, then it means that all the paths that cross 4 will have 4 in them. So how many paths are there which cross 4? This is one path, this is another path, and both the paths have 4 in them. So what I'll do is whenever I am at a node, I'll put that node in an array. or in a list or in a vector, whatsoever you want. Okay. And after putting that in a particular list or vector, I'll make a call to the left subtree and I'll make a call to the right subtree. And while making those calls, I'll pass that vector or I'll pass that list. Okay. This is the idea that I'm trying to convey. So let's just take a quick example. I'll draw. So look at this particular tree. What I'm going to do is I'm going to make a call at this particular node. When I make a call at this particular node, let me draw it. Let's say this node is 3. And I'll pass over here an empty list, an empty array, whatsoever you say. Okay. And now, because I am at this node 3, I know for sure that all the paths that passes through 3 will be having 3 in them. So the first thing I'll do is I'll push this 3 in this vector or array, whatsoever you say, and then I'll make a call to the left child and the right child. So when you push this 3 inside this, you will have 3 over here, and then you will make a call to the left child, which is 4. Okay. And then you will also make a call to the right child. So 3 has been pushed and the right child is this 2. Now I'll keep doing this thing in a repeat mode. So when I am at this node 4, I know that all the paths that cross this 4 will have 4 in them. So I'll push this 4 in that vector. And that way I'll have 3, 4 with me, and I'll make a call to the left and right child of 4. So you make a call to the left child, you make a call to 5, and now you have 3, 4 with you. Similarly, you make a call to the right child, you go to this 7 and you have 3, 4 with you. You know, this is how I'll keep going down. Now again, when I am at 5, I'll push this 5 inside it. Okay. And after pushing 5 inside it, I'll make a call to the left and right. So I'll push this 5, I'll have 3, 4, 5 here. And the left child over here is null, where maybe I can terminate. So this is the idea that we'll be trying to use. We'll have a vector with us. In that vector, we will push the current node, and then we will pass that vector to the next recursive call, which is to the left subtree and also to the right subtree. This is what we'll keep doing. Is it making sense? How many of you are getting the idea here? Okay. However, there is an important thing that I wish to tell you. So if you are using a vector, have you guys learned a little bit about backtracking? The basic idea of backtracking is that if you are doing something, you also have to undo that thing. Okay. So it means that, see, when you are at this node, you are pushing this node inside this list. When you have pushed this node inside this list, you make a call to left, you make a call to right. That's totally okay. Now you are at 4, you push this 4 inside this list. And then you make a call to left, you have 3, 4 at this 5, and you make a call to right, you have 3, 4 at this particular thing. Now, when this particular recursive call is over, should you not remove this 4 from the list? Because when this call is over, you will come back over here. And when you come back over here, you will start considering these paths that go in this direction. Now, the paths going in this direction will not have 4 in them. So it's your responsibility to remove 4. So whenever you are at a node, the first thing you do is you push that node. And after pushing that node, you visit the left subtree, you visit the right subtree. So far, everything is okay. But once you have visited all the paths that emanate from that node, now it's responsibility to pop that node, because if you do not pop that node, that will be reflected in the other paths as well. Is it making sense? Yeah. So this is exactly what backtracking is. You do something. So pushing is like doing something, and then you make your recursive calls, and then you undo that thing. Undoing means, in this instance, you just pop that particular node. As simple as that. So this is what we'll be doing.